Hello everyone, and welcome to the Finance and Risk Corner. If you're liking the videos so far, I'd be very grateful if you hit the subscribe button and turn on notifications. Today we'll explore the binomial distribution. But before we do that, let's demystify the concept of probability distributions in general. So what is a probability distribution? It's a formula, an equation, that gives you the probability of occurrence of a given outcome or a range of outcomes for a random variable. A random variable is a variable the outcome of which cannot be known in advance. Like when you throw a dice, you cannot know whether you'll get 1, 5, or 6. The return on a stock next year, the GDP of a country, or the quantity of rain in a given month are all random variables because you cannot know the outcome in advance. So imagine you throw a dice. So what is the probability that you get 3? We know that the probability is 1 over 6 because we have 6 possible outcomes, and if the dice is fair, then the probability of each outcome is 1 over 6. Think of a probability distribution as an equation where you input the desired outcome, and the output of that equation is the probability for that outcome to actually occur. A random variable can be discrete or continuous. A discrete random variable is one that can only admit a limited finite number of possibilities. Again, like when you throw a dice. There are only 6 possible outcomes, no more, no less. A continuous random variable is one that can accept a virtually infinite number of possibilities, like the quantity of rain or the return on a stock, which can be 12.6459 or 12.6458, or virtually a limitless number of different possibilities. Let's take a simple example where we throw a dice. So what is the probability distribution for that random variable? This is very simple because the probability of the random variable, i.e. the value that you would obtain when you throw a dice, the probability that this random variable equals any number x between 1 and 6 is equal to 1 over 6. This is the probability distribution when you throw a dice. The probability of getting 4 is 1 over 6. The probability of getting 6 is 1 over 6. So if you replace this small x by any outcome that can actually exist when you throw a dice, for example 6, the function would still tell you that the probability is 1 over 6. Random variables have probability distributions when you can write an equation that can show you the probability of any outcome that this variable can take. Now look at the graph. When we look at a distribution, we can think of it as a function. Of course, math is a language, and we can write in numbers what we say in words, but we can also represent this distribution graphically. Now, if you look at that graph here, it is always that on the x-axis you have outcomes, i.e. all the possible values that the random variable can take. In the case of a throw of a dice, it's 1, 2, 6. And on the y-axis, you have the probability for those outcomes to occur, or for other types of distribution, the density, which is used to actually solve for the probability. In all cases, you will look at each outcome, and the graph will show you the probability of that outcome actually occurring. So when you throw a dice, the probability that the outcome 1 occurs is 1 over 6. The probability that you get a 4 is also 1 over 6. So this is represented by a flat line to tell you that the probability of any outcome between 1 and 6, but of course without decimals, is equal to 1 over 6. Now, what is a binomial distribution? A binomial distribution is an equation that will allow you to find the probability of a given outcome, but that is only used for special types of random variables. We call them Bernoulli random variables because those are random variables that can take only one of 2 possible outcomes, like success, failure, or right, wrong, or 1, 0, odd, even. Any random variable that can take on one of 2 possible values, a binary random variable, will actually be modeled, or its probability will be modeled by using the binomial distribution. So the binomial distribution would give you the probability for a given number of successes or failures for a given number of n trials. An example will make it much clearer. Imagine you pick up the phone and you call people and you try to sell them laptops. the probability of success for each call is 30%. Now you need to recognize that the random variable can take on only two possible values. You either succeed in making a sale or you fail. This makes it a Bernoulli random variable, and we need to use the binomial distribution to calculate the probability. So when asked questions such as, what's the probability of succeeding in selling 3 laptops when making 10 phone calls? Or what's the probability of succeeding 5 times when making 5 phone calls? This is where we use the binomial distribution. Always remember, when the random variable is binary in nature, i.e. it can take only one of 2 possible values. Let's work with an example. So you call people on the phone to sell laptops. Again, this is a Bernoulli variable. You can either succeed or fail. Knowing that the probability of success is 30%, what's the probability of succeeding in selling exactly 2 laptops when making 5 phone calls? There is a formula that is quite long and appears to be quite intimidating, but you'll see in a few minutes that it's a very easy formula. This formula we can use when we have a variable that is binomially distributed by doing the following. So we look at the probability of success and we raise it to the power equal to how many times we want to succeed. So in our question here, we're asking, what's the probability of succeeding twice when making 5 phone calls? So this is the probability of success raised to the power 2 because we want 2 successes out of 5 trials. And then it is multiplied by the probability of failure, which is raised to the power 3, which is the number of failure attempts. When saying that we succeed twice out of 5, this means that we will fail 3 times out of 5. And then this is multiplied by a combination of 5 choose 2, and the answer of that equation is the probability of succeeding exactly twice when making 5 phone calls. Now, what's the probability of succeeding 0 times when making 5 phone calls? It is 16.81 if you use the binomial distribution. The probability of succeeding exactly 1 time when making 5 phone calls is 36.015. Now notice how the formula goes. Look at the probability of succeeding 4 times when making 5 phone calls. It is the probability of success raised to the power 4 because we want to succeed 4 times out of 5, multiplied by the probability of failure raised to the power 1 because we want to fail 1 time out of 5, and then everything is multiplied by a combination of 5 choose 4, which would actually give you the final result of 2.835%. Now I want you to notice that if the probability of success when you make each call is 30%, it's a constant probability of success, i.e. every phone call is independent and has the same probability of success, which is 30%, then the expected number of successes is actually 5 multiplied by 30%, which is 1.5. When you attempt 5 phone calls, given that each phone call has a 30% probability of success, then the expected number of successes is 1.5. Another example would show how intuitive this idea. Imagine you attempt 10 phone calls with a 30% probability of success, then you would expect on average 3 successes. Of course, in real life, you can't succeed 1.5 times. You either succeed in selling the laptop or not. But the important point is to recognize that the expected number of successes is 1.5, given that you're trying 5 times and the probability of success for each attempt is 30%. Now this is important because if you look at the graph that represents the different probabilities for different potential outcomes, you would see that the 2 outcomes with the highest probability of occurrence are 1 and 2. Why? Because they are very close to the expected outcome, which is 1.5. Given the probabilities, if I make 5 phone calls, I expect 1.5 successes. If I make 10 phone calls, I really expect 3 successes. Now, given that, the probability of succeeding once out of 5 trials has the highest probability. The probability of succeeding twice out of 5 trials is also very high. Now notice that as you get far away from the expected number of success, which is the theoretical 1.5, the probability starts to fall dramatically. The probability of succeeding 5 times out of 5 when you actually have a 30% probability of success for each trial is very, very low. It is only 0.243%. Now let's understand the formula and how it is structured. Back to our example where we are calculating the probability of exactly 2 successes out of 5. Imagine you have no binomial distribution formula and you're really thinking about it. So what's the probability of succeeding twice out of 5 trials? At the first attempt, or on the first attempt, the probability of success is 0.3. On the second attempt, the probability of success is also 0.3. Now remember, you are calculating the probability of 2 successes, which means you must know 3 failures. So the probability of succeeding in the first and second attempt is 0.3 multiplied by 0.3. Then now the probability of failing for the third attempt is 0.7. For the fourth attempt, it's also 0.7, and for the fifth attempt, it's also 0.7. It's easy to recognize that you can rearrange this formula to have 0.3 power of 2 multiplied by 1 minus 0.3 to the power 5 minus 2. In simpler language, this is the probability of success raised to the power of how many times you want to succeed, multiplied by the probability of failure, 1 minus probability of success, raised to the power of how many times you want to fail. So succeeding twice out of 5 means that there are 3 failed attempts. By the way, we have reconciled this part of the formula. This is exactly what it is. It is the probability of success raised to the power how many times you want to succeed, multiplied by the probability of failure raised to the power how many times you want to fail. Now, what is this combination here doing in this formula? To understand this, first recognize with me that if we write this and we stop, it is as if we're saying, remember math is a language, it is as if we're saying there exists only one way in life to succeed twice out of 5 trials, which is to succeed on the first 2 attempts and then to fail the remaining 3. In reality, you're going to have to admit it, of course, there are more than one way to succeed twice out of 5 trials. This is one way, but this is another way. You could fail the first 3 attempts and then succeed the remaining 2. Or this is a third way. You can succeed and then fail and then succeed and then fail twice. Or you could actually succeed once and then fail twice and then succeed once and then fail again. All those are different ways where you can succeed twice out of 5 trials. So if you write this formula here and you stop, it is as if you're saying there is only one way and one way only to succeed twice out of 5 trials. In reality, you need to count the different ways that exist to succeed twice out of 5 and then multiply those number of times by this formula here so that you get the full picture of the total probability. So the combination here is actually doing the hard work for you. Instead of manually counting all the different ways by which you can succeed twice out of 5 trials, the combination will do that for you. Let's make sure that it does it and understand how it does it. So a combination of 5 choose 2 is actually 5 factorial, right? Divided by 2 factorial multiplied by 5 minus 2, i.e. 3 factorial. A factorial is when you multiply the number down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. You'll see why in a second. And then you have 2 factorial multiplied by 3 factorial. Those will cancel out. You can simplify further and you get 5 times 2, which is 10. There are 10 different ways to succeed twice out of 5 trials. So back to our formula. What is the probability of succeeding exactly twice out of 5 trials? Even if I don't know the binomial formula on the exam, that's what I would do. So the probability of succeeding twice out of 5, first I need to succeed twice. This is the probability of succeeding twice. Or I also need to fail 3 times. So this is the probability of failing 3 times. Then I will stop and recognize that if I stop here, I would be saying there is only one way to succeed twice out of 5 trials. I now know that there are 10 ways. So all of this is multiplied by 10, and I have my result, which is 30.87%. That's the probability of succeeding twice out of 5 trials. Now you understand why the formula is written in this way and what is the role of the combination. It is counting all the possible ways to succeed twice out of 5. Now, one remaining question is to understand how is the combination actually succeeding in computing all those possible ways of succeeding twice out of 5. And to understand that, let's depart a bit from the example and give a simpler one. Imagine you have 2 chairs, A and B, and you have 5 individuals, 1, 2, 3, 4, 5. So individual number 1, individual number 3, right? Instead of writing names, and you are interested in all the number of possible ways by which you can seat 2 persons out of those 5 on those 2 seats. So how many ways do you have, different ways, to seat 2 people out of those 5 on those 2 chairs? You could start to count them manually. It would take you a lot of time. You could seat 1 and 2, 4 and 5, 2 and 5, 1 and 4. You could count all those different possibilities and then come up with a total number. Or you can simply use a combination when the order doesn't matter. When I say the order doesn't matter, it means that if you seat 1, 2, it's exactly as if you seat 2, 1. So if person A sits on chair, if person 1 sits on chair A and person 2 sits on chair B, it's exactly the same as if person 2 sits on chair A and person 1 sits on chair B. It's the couple 1, 2, same 2 people. So you should not double count them because the order doesn't matter. Whether it is 1, 2 or 2, 1, it's the same combination of 2 different individuals. So again, how is the combination capable of actually coming up with the solution so brilliantly? It is a very powerful tool. Now look again at the formula and you'll understand what's going on. The formula is 5 factorial. So excuse me for that. The formula is 5 factorial divided by 2 factorial multiplied by 5 minus 2 factorial. To understand why it's written this way, math is a language, let's start by doing something nice here. Let's assume we have 3 remaining chairs. I'm changing the color on purpose because those chairs do not exist. Remember that the question is, how many different ways do we have to seat 5 different people on 2 different chairs? I'm going to start by imagining that I have exactly as much chairs as people. So I'm drawing 3 additional chairs but in a different color. And now I invite you guys to think about it because you'll gain a lot by understanding the formula. So how many different ways do I have to seat one of those 5 people on chair A? I have 5 different alternatives. I could seat person 1 or 2 or 3 or 4 or 5. I have 5 different alternatives to seat one of those 5 people on chair number A. Once chair number A is full, how many different ways do I have to seat someone on chair number B? Only 4. Because one of the 5 people is already on chair A, so I now have 4 possibilities to choose from to fill chair number B. Same goes for chair number C, let's call it D and E. The total number of ways that I have to seat 5 different people on 5 different chairs is 5 times 4 times 3 times 2 times 1. Guys, this is the 5 factorial. Now, of course, you're saying, but the question is, how many ways do you have to seat 5 people on 2 chairs? Why did you assume you had 3 hypothetical chairs? You'll see, because that's the easiest way to solve it mathematically, and it works for any possible question that you can think of. Now, again, the numerator is explained by the possibilities, all those possibilities to seat 5 people on 5 different chairs. Now think about it. Do you have 5 different chairs? No, you have only 2. So once the first 2 are actually full, you don't really care how many ways you have to fill the remaining 3 hypothetical chairs. So there are 3 times 2 times 1 different ways or different combinations that you actually don't care about. Because one more time, I remind you, the question is, how many different ways do you have to seat 5 people on 2 chairs? So all those different ways to seat people on the remaining 3 chairs that don't exist, you don't care about them. And how many ways do you have to seat people on the 3 chairs you don't care about? 3 times 2 times 1. 3 factorial. Coincidence? No. This is this part of the formula. Now we're not done, because there is a 2 factorial here. This one is the one I explained earlier. You have 2 chairs now. Imagine you chose the couple of people 3, 4. You could seat 3 on chair A and 4 on chair B, or 4 on chair A and 3 on chair B. It would make them the same couple of individuals that you chose, i.e. 3 and 4. So you should not double count those 2 options. In reality, they are one option. But you have 2 different ways to seat 2 people on those 2 chairs A and B, but you know that's double counting, so you need to remove them. Hence the 2 factorial that exists here, which is simply 2 times 1 equals 2. So look again at the formula and understand how brilliant the formula is. The numerator starts by computing all the possible ways you have to seat 5 people on 5 chairs. Then the numerator enters to refine the process by saying, first, I don't need the possible ways to seat people on the 3 chairs that don't exist, so cancel them out. That's the role of this part of the formula. Then the numerator does an additional final adjustment. The denominator, recognizes that there are 2 possible ways to seat the same 2 individuals on those 2 chairs, and we shouldn't double count them. So we remove them in the denominator. Now look how the final answer is doing exactly what I'm explaining. 5 factorial is 5 times 4 times 3 times 2 times 1. This is the formula mathematically in math language saying, those are all the number of ways to seat 5 people on 5 different chairs. Then the denominator enters and says, I don't care how many ways you have to seat people on the last 3 chairs, because they don't exist, I don't care about them. And notice how those offset. So the number of possible ways in the denominator falls back because we have 2 chairs and not 5. We're not done, because the denominator does something else. It recognizes that on chairs A and B, i.e. the 2 chairs that actually exist, you have 2 different ways to seat the same 2 people. And you shouldn't double count those 2 different ways, because that's one combination, you have the same 2 people. And this is the 2 here that is doing this job. Now 4 and 2 would actually simplify, and the total number of ways is 10. This is exactly what's going on in our formula when we calculated the total number of possible ways to succeed twice out of 5 trials. Now this can be applied to when you play the lottery. So imagine you have 42 different numbers and you want to pick 6. So how many different combinations of 6 numbers do you have when you have 42 different numbers, right? This will instruct you, this will make you understand that the probability of winning the lottery is extremely small. And hopefully we need to study and work, right? Instead of counting on the lottery. So you have 42 different numbers. What are the total number of different combinations of 6 numbers that you can have? Of course, the order doesn't matter. i.e. you still win the lottery if the numbers 1, 2, 3, 4, 5, and 6 are drawn, even if you chose 6, 4, 3, 2, 1, and 5. The order doesn't matter. This and this are considered as one alternative. So what are the total number of possible ways by which you can form 6 numbers out of 42? It's a combination of 42 choose 6, and look again how the formula is thinking. 42 factorial is the total number of ways by which you can have 42 numbers aligned differently, right? 42 factorials. But I'm not drawing 42 numbers, I'm only drawing 6. So whatever happens after this first 6 numbers are drawn, I really don't care about. So 42 minus 6 factorial, i.e. 36 factorial, are all the different combinations that the 7th, 8th, 9th, etc. numbers are drawn, which I don't care about. But we're not done. Because even the 6 numbers that are drawn when you play the lottery, there is a 6 factorial way by which they can be drawn. They can be 1, 2, 3, 4, 5, 6, or 6, 5, 4, 3, 2, 1, or 6, 4, 3, 2, 1, 5, etc. The 6 factorial is actually counting all those numbers. And if you calculate this, then you would get 5,245,786. So when you play the lottery, if you pick one combination, right, you have one chance out of 5.245786 possible. So it's one chance out of 5.245 million different combinations that could exist to win the lottery. This is why we need to study. And I hope this channel will actually help you to study. So that was it for the binomial distribution. I hope things are now much clearer. You don't need to memorize the formula. The formula is very simple, very basic. The probability of success raised to the power how many times you want to succeed. Probability of failure raised to the power how many times you want to fail. And then you need to adjust by the total possible number of combinations by which you can fail X time out of N trial. So again, I'd be very grateful if you hit the subscribe button, you turn on notifications so you're sure to be the first one to know when we release new videos. And as always, please don't hesitate to send your comments, questions, or any proposals you might have, any suggestions regarding the future topics that I would cover in future videos. Thank you again.